This evening. So we're going to, after the talk that ends at 4, there'll be an hour break, and then there is a panel at 5. That's part of the Theoretically Speaking series. It's a general public targeted panel that we're kind of taking advantage of the fact that we have great people here this week. So you're welcome to stick around for that afterwards. So our first speaker this afternoon is Dileep George from Google DeepMind. Dileep was founder of Vicarious, which I think a lot of you have heard of, kind of an AI startup in the kind of more cognitive space. And he also kind of came up with the idea of a hierarchical temporal memory, which is a kind of important connection between AI aspects and cognitive aspects. So he's going to give us a different perspective on transformers. So great to have him here today. Thanks.
Thanks, Sasha. Thank you for having me. Thanks to Anil for connecting me to Sasha, and thanks for the invitation here. This is going to be a different kind of talk than the ones that you've seen in this one. There will be a bit of neuroscience, cognitive science, sequence learning, transformers, and philosophy. So let me just dive in and tell you why it is relevant for transformers and sequence learning. So cognitive maps is mostly experiments done on humans and animals, mostly on animals, where rats can be put in mazes and they will learn the layout of the maze and then can take shortcuts in that maze, etc. And the classic experiments in this area was done right here in Berkeley by Tolman. And this is the Tolman maze. And oops, my internet is not working, this means. Hold on a second. All these slides have pictures. Are they showing up there? Okay, they are showing up. Okay, cool. So this is a classic experiment where Tolman just let rats run in a maze. The title is a bit anachronistic, but just deal with it. And even without any reward, the rats are just running around in the maze, and they are not exposed to any food. They're not searching for food. They're just running around, and then they suddenly introduce food in a particular location, in the food box on the 10th day, and suddenly, very quickly, the rats can reach the food and without any error. Whereas the rats that are introduced to food very early on, gradually get there. So even though there is no food, the rats are still learning about the layout of the maze. And once the food is introduced in a particular location, they can quickly find the way to that from any other location in the maze. That's because the rats do this thing called latent learning, where they, even without any reward, they are learning the layout of the maze. And related to this one is this Nobel Prize in Physiology in 2014 was about rats learning mazes. And the discovery here is that there are cells in the hippocampus of the rat and also in humans that light up when rats are in specific locations in a maze. So if you put a rat in a box and start recording cells from the hippocampus, there will be specific cells that light up when the rat is in location XY. So X1, Y1, and one cell lights up, X2, Y2, another cell will light up. And which is kind of mysterious when you think about it, right? Rats do not have GPS. So there is no location coming in the sensation anywhere, but they will respond very strongly to specific locations in the environment. And this was kind of a big deal, discovering this thing called place cells. It is actually called place cells. That's the name given to that. And it was a big deal, and it is called, this is the GPS in the head, et cetera, et cetera. But then anomalies started adding up, because initially it was thought that these cells were responding to just the location. But then there was this discovery where, it's actually not responding to location. So if there is a central arm and the rat is going to turn left versus right, the central arm where it's taking the common route, there will be cells responding only when the rat is going to turn left in the future. And another set of cells will respond to cell, it's in the same location, so there'll be two cells, one for the left turn and the other for the right turn. So it's not just responding to places anymore, it is responding to, where the rat is going to go. So these kinds of, and if you have not just places, you can also expose rats to smell sequences. And if there is an overlapping arm of this smell ABC, where it's coming from one set of smells and then going to another set of smells where there's overlapping arm, these smells will take different representations in the representation space. So these are all things that started adding up, which changed the story of what these place cells mean. Like, in fact, if you read this hippocampus literature, there's phenomena after phenomena being discovered. New kinds of cells. It's not just place cells. It is corridor cell, door cell. Pretty much any cell you can think of is kind of discovered there. And there was no coherent theory. In fact, if you take the hippocampus book, it's like 3 inches thick, and it's full of this phenomena called splitter cells, event cells, landmark cells, vector coding, etc. Whereas the original story was very, very clean. It was place, but it's not place anymore. It's a whole bunch of the soup. And then until we came along and we kind of change the story around based on other people's work, but we put a coherent model there. And we recently published this paper called Space is a Latent Sequence. O'Keefe's original discovery of place cells was kind of a misnomer. The rat was not responding to location. The rat was just learning sequences from sensory observations in that visual environment. And the rat was not responding to a particular location. The rat is responding to the sequence of sensations that drive to that location. And if you model those sequences in the right way, then it will look like it is responding to locations. But it's not. It's really just the sequence of sensations that drive to that location, which is two different things, right? Responding to location is different from responding to the sequence of sensations that drive to a location. And if you change that around, then all these variety of phenomena that look different, this splitter cells where it going left versus right, that suddenly makes sense. All those overlapping orders, they start making sense. So this list that I had here were the list of phenomena that we explained in our paper using basically, it's not this hippocampus, this organ that people thought of as modeling space has nothing to do with space or very little to do with space. It's really just a sequence learning model. And if you just learn sequences in a latent space, then those sequences will end up representing locations. The latent variables will correspond to locations. And that's what when you measure, it looks like it is responding to locations, but it's really about sequences. And that's why people who are working on sequence learning should care about hippocampus and cognitive maps. And recently there was this very pleasing paper published in Nature where they again ran some experiments on animals. And so our model is called clone structured causal graphs. I will explain that in a second what that means. And they ran some experiments on how rats learn state machines in a virtual world. And the dynamics of that learning was explained much more accurately by our model compared to LSTMs or transformers, although they were also able to predict the next observation very well. The learning dynamics matched our model much better. Yeah, go ahead.
A question about the model of the hippocampus. How does it interact with the seemingly 2D structure of the grid cells in the hippocampus?
Okay, so you know about grid cells. Okay, so so there is this other, so hippocampus gets an input from a part of a cortex called entorhinal cortex. And so entorhinal cortex has this thing where the neurons there respond periodically to space. So it's like this. So this part of the brain is getting input from your vestibular sense. It's just your self motion sense. So if you close your eyes and somebody moves you around, you can still get a sense of your motion. And by integrating this self-motion thing, you can kind of periodically tile the space around you. It's just a local motion cue that you have, and this part of the cortex that encodes this produces this set of cells called grid cells, where the neuron will fire here, and then neuron will fire a little bit away from here, and then if you then periodically, it's like a periodic tiling of 2D space. This periodic tiling of 2D space is not extremely useful in representing space because because it's just periodic. It's not unique. It doesn't uniquely represent a space, but it is useful for sequence learning model. If you take the sequence learning model and put in this periodic signal, it just helps disambiguate areas where there are less contrasting sensations. It'll probably become clear when I go to the next few slides where the grid cells come into play. Although I don't have any slides on it, I'll just verbally try to explain it. Okay, so let's look at what's a sequence learning problem in the representation of space. So here is a typical 3D maze where we run rats or simulated agents, and what the organism is getting, the agent is getting, is just the views, the visual frames from the environment. There is no GPS or anything, and from that it has to learn the structure of the maze. And the problem here is that the sensations are aliased. The same sensation can occur in different parts of space. So that's really the problem. And if you put that in a 2D, very simplified computer science view, it's like the rat is sensing the color in that location, and it is running around making actions in that 2D room. And so the sequence that you're getting will go gray, 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 green, 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 like that for a long time without really telling you which location you are in. And you are not allowed to make any Euclidean assumptions, because the world that the rat running need not be Euclidean. There can be shortcuts, there can be teleportation, etc. In a virtual environment, for example, if you make and they can learn this teleportation shortcuts if you put rats in a virtual environment, and it's definitely non-Euclidean because you can be running in cubes, not in 2D planes. And from this one, our model can learn the structure of that environment, like in the graph form. And why are there 4 nodes here, for example? That's because in a particular location, the rat can be in 4 different heading directions, and those 4 different heading directions are also induced by the model. So these nodes, the 4 different nodes correspond to the 4 different heading directions that are in that particular location. And this doesn't depend upon the topology where the thing is coming from. It can be, the rat can be running on a cube or a sphere, doesn't matter, and there can be non-Euclidean shortcuts, etc. And you can expose it to 3D environments of varying complexity. And I am laying out this in 2D, but it's just a graph. There is no layout associated with it. I'm just using a particular 2D layout to plot it, just a graph. And the model here is super simple, especially compared to a transformer. But there are some nice properties of this model. So this is an overcomplete HMM at the very core of it, where the number of latent states is way more than the number of observations. So the observations are the colors that you're seeing in the room, and the latent states are 100 times or 1,000 times more than the number of observations. And we impose a very specific structure on that. That is, we take a set of latent states together, and we call them clones, and they are hardwired to emit the same observation. So the emission matrix here is not stochastic, it is deterministic. So these set of clones are hardwired to emit the same observation. Without that assumption, without this, if you keep the emission matrix completely stochastic, then it's a fully general HMM, and then it doesn't learn. It just gets stuck in a local minima. This kind of structure, it's kind of a convolution, but in the latent space. That assumption is crucial to make it learn this structure. And once you do that, you can learn the transition matrix here in a very sparse form, and it returns a graph, and it can be directly interpreted as a graph because the connections from the latent states to the emissions are not stochastic, they are deterministic. And of course, this is just the very basic story. Here, of course, you have actions instead of just transitions. So you have to take that graphical model and change it to include the actions. So it becomes a POM-DP with a specific structure. And if you want to model environments which are rich 2D structures, then you have to put a vector quantizer in front of it. So it's a latent state, conditioned on action with a clone structure here, deterministic emission, vector quantizer, and the image. That's the model. Okay, so let me, I don't have a slide for it because I usually give this talk in those slides in the neuroscience talk, but let me just explain what these place cells mean, right? So remember there were cells in the rat's brain, in the hippocampus, that respond to locations. And the same thing would happen in our model too. These cells, they can think of each of these nodes here as neurons. And each of these neurons are actually responding to, it will, if you measure, if you do the experiment that the neuroscientists do, it will look like these neurons are responding to locations. Do you know why? It's because the way the neuroscientists do these experiments is they put a rat in that arena. So they'll put a rat there and let the rat run around in that arena. And they are recording from a particular neuron. Let's say we are recording from this particular neuron. And they're just letting the rat run in that room. And whenever this neuron fires, they will put a dot in that part of the room. In a plot corresponding to the room, they'll put a dot there. So you can see when will this neuron light up. This neuron is responding to just the gray color. But it will respond to the gray color only when the rat takes any of these particular sequences that gets there, right? Because in the latent space, it will respond to the gray color only when any of these sequences that lead there happen in the observation space. So that's why this neuron will look like it is responding to this particular location when you do this neuroscience experiment. But in reality, this is just a sequence model. The layout comes purely from the visualization. This is purely a sequence model. There is no geometry in it. Yeah.
You're suggesting that the place cells are like highly path dependent.
Yes. And yes. Oh yeah, this is exactly the test that people have done to come up with this phenomena, right? For example, if I take this rat and constrain it to run only left to right in this world. Suppose you impose this artificial constraint that I'm going to let the rat run only left to right. These cells will be direction sensitive. They will fire only when they go from left to right and not from right to left. And you can see this in animals. And this is also the other thing where the rat was going left versus right to the central arm. There will be one set of cells which are responding when the rat is going left, and the other set of cells when the rat is going right. So you can see this sequence dependency in actual animals. And it's just that when the rat is taking a random walk and learning, and then when you test it using a random walk, it will look like, oh, it is responding to the location. But anything other than the random walk, it just responds to the structure of what that sequence was. Okay, and now the grid cells. So here, imagine that I made this room much bigger. That is, I get a lot of gray color, but I get distinguishing inputs only at the boundaries. So as you make this the center of the room bigger, the learning will degrade because it's just getting gray, gray, gray for a long time. And your sequence learner will barf at some point and won't create enough latent states to keep these contexts separate. So the center of these things will start collapsing. The graphs will kind of start deforming. And grid cells are a augmentation to kind of get around it. So it's like instead of this uniform space, your self-motion cues will at least tell you that, oh, you moved from the previous time step. Even if you are blind, you can, even if you're close to your eyes, there is a vestibular sensation that gives you this additional information that, oh, you are in a different location. And it's more than that, because that vestibular sensation can be used to create a periodic tiling as you're moving in space. So imagine that instead of gray, you are getting one here, then again one here, and again one here. It's a periodic tiling, which helps you learn the sequences when there is no other sensation available. So that's the way grid cells work. And there is experimental evidence that even if you turn off the grid cells, rats are usually just normal. They're fine in learning mazes, even if you just kill the grid cells totally. So most of the work is done by sequence learning. This additional vestibular sensation is just an augmentation if you have no sensation, if you're walking in the dark room, etc. Okay, so having this latent graph has some advantages compared to pure. So, for example, an RNN or a transformer can learn to predict the next one. And if you measure the latent representations, you will actually see place cells. So because now we can explain space as just a sequence. You can use a transformer or an RNN or anything in LSTM to get these place cells in the model. But having the latent structure as an explicit graph has a few advantages. One is planning, because since the world is partially observable, if you want to plan, just random sampling and trying to go to a location is extremely inefficient, because you're just multically sampling, and you won't even know when you hit the target location, because there is no it's just specific sensations you're sampling. Whereas if you have the latent structure, oh, this is the latent node that I want to go to, and you have the graph, you can directly use a path planning algorithm or message passing. Another one is rapidly adapting to and modifications of the environment. So if I have this graph, and one link in that graph corresponds to passing through a door, and if I now walk into an environment and find that, oh, that door that was open is now closed because I can't go through it, it's a very quick modification that you can make in the model. If you have the graph, you can just modify that graph, and now you can find a new path to walk in that environment. Whereas if you don't have that, if that model is kind of spread around in a way that you can't access, then you can't make that change. And of course, then there is this idea of transfer learning, where you can use that graph and impose that knowledge somewhere else. I have an example of that. And you also have the advantage of attaching episodic memory on this latent structure. Episodic memory is our memory of what happened where. Oh, I came here this morning and I got coffee. And that location here is a latent node. And you can layer that memory and attach it to that latent node. And you can then attach a timestamp onto that latent node. So you can very easily layer episodic memory if you have a latent structure. So let me explain some of the. I won't be able to expand on all of them. At least some of them I'll be able to expand. So navigation. So this is just a video showing that using this latent structure, it can. Usually when people talk about hippocampus models, they just show the place fields and the story is over without the model actually doing anything. Here, this is just showing that, oh, we can actually use this model to learn an environment and walk there and reach a goal. Oops. Okay, now let me talk about transferring this latent structure to learn a new environment. So imagine that the rat has learned a room, and it has green carpet and pink and green walls, etc. And it has learned the structure of that room in this latent graph. This latent graph. Okay, that's not the pointer. Okay. Okay. So this latent graph here. So this graph I'm just laying out in 2D here. It's the same graph, and I'm just emphasizing the clone structure here. These are all the latent nodes corresponding to this observation green. So these all the different green observations coming here gets mapped onto different latent nodes here, which are laid out in this form when you actually lay out in the 2D graph. But it's really a graph. Now, if I take this latent graph and disconnect it from the observations, then what you have is a graph. It just doesn't have any observations connected to them. But it still has some structure to it. It still encodes the overall geometry of the room. It just doesn't know which observations it is connected to. But it still has information that, oh, all these nodes are supposed to connect to the same observation. You just don't know which observation it is supposed to connect to. So there's a graph with slots in them. And so that means now if I go to a different room which has the exact same structure but different color of carpet and walls, then instead of trying to learn that room from scratch, I can just learn the coloring, which is basically saying I can just learn this emission matrix instead of learning the graph structure to begin with. So that's just learning the coloring here. So you just learn this emission matrix, which is way faster than learning the transition matrix, this latent graph there. So that means this idea of learning cognitive maps can be turned around a bit, which is, so if you have experience with a large number of environments, you take those specific experiences and disconnect it from the actual observations and keep it abstract. So this is called schema. This idea in cognitive science is called schemas, where you take this specific experience you had, but you abstract it, disconnect it from the actual observations. You are keeping around a bunch of schemas, and then when you come to a new environment, and this new environment might not be an exact fit. It doesn't need to geometrically exactly fit. This graph can be slightly different. The graph of that environment can be slightly different because probabilistic smoothing can take care of a whole bunch of size variations in the graph. So when you come to this new environment, instead of trying to learn the graph of the new environment, you are trying to find out which schema does it match well. So you are trying to learn n emission matrices at the same time. So if you have these emission matrices, you can learn n emission matrices at the same time to see, that coloring matches better than any other coloring. So you can recover the schema corresponding to a new environment like that. So, and you can go beyond that if you are, yeah. Yes.
I think I'm confused about how the model works. Like, can you explain again what the clones mean? And, compare it to a ML model.
Just think of it as this is a standard Hirschmarkov model. Just think of so this is the latent space. All the clones are in the latent. These are the latent nodes. These are the observations. So it's a Hirschmarkov model, except for with this additional wrinkle that in a standard Hirschmarkov model, any of these nodes can emit any of these nodes. A probability of emissions given for a particular state is completely stochastic in a standard Hirschmarkov model. Here, all we are saying is that these set of nodes, hidden states, is restricted to emit only this emission. There is no stochasticity. And these set of nodes are restricted to emit only this one. And this is a constraint we put during the learning. We basically say the emission matrix is fixed with this structure. And all we do is we just do standard expectation maximization learning when the rat is walking around in this room. And it will wire up this latent graph. And it will induce this. So these nodes will take up. This node will basically say, okay, I'm going to represent this part of the thing, and if there are head directions involved, it will take up these different head directions. Does that? Yeah.
Emission is fixed.
Yeah.
And it's one-to-one.
Emission is not one-to-one in the sense that it's many-to-one. Yeah, multiple hidden states can emit the same observation. Okay. Yeah.
In an HMM, the hidden chain usually. There are vertices here with n degree greater than 1. aren't there?
No. In hidden Markov model, it's not. It's the transition is just stochastic. Anything can go anywhere. Yeah.
Oh, I should think of this not as the random variables, but the state space itself.
Exactly. Yeah.
Before you were implying there was a factorial HMM, that there were like many hidden states. Is that true as well?
Here, no, it's not factorial. No. This is just a standard single chain HMM. Yeah.
So when you draw one of these arrows, that just means the probability of that transition is high.
Yeah. So here, I am. So what might be confusing is that this whole thing is one random variable, one time step. Like I am showing the contents of within that random variable.
But how are you enforcing it?
So we are enforcing it through a procedure. So the way we are learning is we first do standard EM on this one, and at the end of the standard EM, we just do a Viterbi EM, and that just makes it sparse. Yeah. Okay. Hopefully that makes it a little bit clearer. Yeah. Okay, so let me come here. Okay, so now when you encounter a new environment, which is and a bigger environment, you can compose these schemas together. So you're trying to explain this environment or model this environment using a whole bunch of schemas that you have, but not using exact one of them. You're going to say, I'm going to put this schema here, and what's the best match here. Remember that this new environment is not exactly any of those schemas. It's a composition of them, and also the color is different. Like the skin is different. It's not any of the things that you have learned. So by using this library and stitching that together, you can represent large environments very efficiently. And if you try to learn it without schemas, it just takes an enormously long time. But with schemas, you can train it much faster. And also it also enables flexible planning through unseen areas. So even if you haven't experienced a part of the area, you can still plan through it. This is like, imagine 2 floors of an environment has the same layout. You walk in the first floor. When you go to the second floor, you can still plan through the second floor, even though you don't know what exactly you're going to see. You will say, there might be different furniture here, but you can still plan a path through that. You are using the layout of the first environment to plan through the second environment. That's exactly the idea here. You're using the schemas from there. So the original observations, you can even say that, I might see different things here. I'm going to walk through unfamiliar area. I might see different things here, but I expect a path still here if it's the same layout. That's the same idea here. Yeah.
How does the concept of the schemas map onto that HMM diagram you were just explaining?
Just take the HMM and remove the emission matrix. That's it. What is this? Just the transition matrix is the schema. And then basically you can take the same transition matrix and attach different emission matrices to that. That's basically Okay. So we had this paper. This might be interesting to people who think about in-context learning in transformers. There is a way to explain some parts of in-context learning using this model. It demonstrates some of the in-context learning things that transformers have, but not all of it. Transformers have are a lot more powerful. So one example of in-context learning is, you give this prompt, and I guess this is reverse or rotate. I don't know what it is, but it will produce this output. Even though these symbols are all new, this is what will happen in a transformer. And the same thing kind of can happen in this model too with an additional modification. So keep in mind that this model can also is a language model, a lousy language model, but it has some nice properties where the clones, this will make sense even better in language in some sense. Locations or sensations are like just words. Just like a sensory observation is a word, and just like the same sensory observation can happen in different locations, different contexts, the same word happens in different contexts, right? Bank can be a bank robber or a river bank, and if you put it through this model, it will allocate different clones to them because of the context. So it is trying to separate these contexts, so they will wire to different clones. And of course, branching, transitivity, all those things happen of a standard sequence model. those things exist in the model. Now, so I explained how you can take this structure and transport it to a new environment. But what if in the new environment, the whole environment didn't change? What if I changed only, I kept most of the environment same, but I changed only, let's say, this wall color. Now, instead of learning the whole emission matrix, again, I can basically say, I will learn only emission matrix when I am surprised. Because when I'm walking in this new environment, most of the time I'm predicting fine. But in some portions, when I hit this wall, I am surprised. I'm not able to predict the observation. So if I can relearn the emission matrix only when I am surprised, then it will be much more efficient than learning the emission matrix from scratch altogether. So this is the idea of rebind based on surprise, and this is there's a word in neuroscience. There's a phrase called behavioral timescale plasticity, where this plasticity is as you are behaving. It's not like it requires a lot of experience. It's happening on the fly, and with that you can get this ICL kind of phenomena in this model. So keep in mind that this model can also learn simple algorithms like parity. It can learn parity, but it will only learn parity specific to that particular symbols that you are trained on. It will learn 0-1 parity. But suppose I want to take this model and let it count A-B parity, where A and B are new symbols. And so here is example. It can learn reverse, but it is tied to just this reverse. It can reverse A, B, C, D, E. But what if I want to reverse some other set of symbols? That's where the idea of taking this circuit and being able to connect this to some other set of symbols come in. That's the rebinding idea. So if you can take this circuit and connect it to new symbols on the fly, it is in context learning. It will demonstrate in context learning. And this is the same idea of emission matrix relearning, except that now we are basically saying these portions of the emission matrix are fixed, and they act as anchors, while you keep this portion of the emission matrix flexible and relearn them. So to demonstrate this, you have to really train the model on a whole bunch of algorithms at the same time. So that's what we did. So this is almost like you can think of an algorithm as a room, right? So because it's just a circuit, right? And a room is a circuit, and you learn a bunch of algorithms here, which are things like transpose, roll the column, circular shift, etc., all using the same model. And they are all like different rooms in the same model. And then you disconnect that from the specific symbols that you learned on. And then you let it run. Actually, you keep the emission matrix around, but you let the portions of the emissions matrix rebind or relearn when you run this in a prompt through. It has to recall the correct schema and fill in for the right binding. So, and that's what really happens when you put this prompt through. In just the first iteration of the EM, it will converge on to, these are the 3 potential algorithm candidates. And the second iteration of the EM will fix the contents of the binding, and then on it doesn't change. So it's with 2 rapid iterations of EM, it is able to locate the circuit and do the rebinding. So it has to do this 2 inference at the same time, which is what happens in ICL, of course we know. So in context learning, at least this aspect of it can be explained as simultaneously inferring the schema or the circuit corresponding to the algorithm and the bindings. Of course, in the transformers, no weight changes are happening. It's all in the activations, because it can be just using the activations to gate a bunch of circuits. In this model, it happens through weight changes. Okay, now coming to transformers. So you can take this same, because it's a sequence learning thing, we can try to get some of these properties from a transformer. And that's what we tried here. And it's a bit hacky, but maybe this will inspire some new work here. So again, the setting is that of a the simplified setting is that of a 2D aliased room. So this is a room in which the agent is walking. What it is observing is the local color. So it is aliased. So you get a bunch of training observations, and you learn a model. And then the idea is that you want to, after learning a model, you want to plan a path from A to B. And if you just have the standard transformer, I don't know how to do it because we are able to predict the next token, but that's not enough, right? You need to be able to, it's not even clear how to say I want to plan a path from A to B because what's given is just the observation stream, not the location itself. Location in the original CSCG model is an induced concept. So in that original model, I can say, for example, if I'm given a stream here, I can, in the original CSCG model, I can always say, go back to the beginning. For example, the agent experienced a sequence of observations. At the end of the sequence of observations, I can say, go back to the beginning. And that's a well-formed question because what the model can do is, run inference on that whole sequence, find the latent state corresponding to this observation, and go back to that. So you can basically say, you take this observation sequence, decode it in the latent space, and then find a path from the latent states corresponding to the end to the latent states corresponding to the beginning. That's a well posed problem in the latent structure model. But in the transformer, we don't know how to do that, right? Because what does it mean, go back to this observation? So if you just do random shooting, there is one way to do it is it's basically saying go back to this observation so that it produces the same sequence in the forward, or you can put a criteria like when it reaches B, you keep the tail, keep a tail of this sequence stored as the context to generate after reaching. So you can basically say, by evaluating whether it produces the subsequent tail, whether it has reached that location or something. That's what we are doing to test. But just using a transformer is not enough to do that path planning problem. So what we did is, instead of using a vanilla transformer, we first trained a transformer and then put a discrete bottleneck on top of it. So we took the transformer outputs at every time step, vector quantized it, and then trained an MLP to predict the symbol, and also put something at the end to predict the next symbol, and in fact next n symbols, to then learn a cognitive map of the same structure. This map has the same structure as the original CSCG map that I showed, where these nodes are latent nodes. They are connected to the same observation, and this is extracted in a little bit hacky way from this discrete bottleneck. So now that you have a discrete bottleneck here, you can, by counting the transitions between the quantization center here and quantization centers here, you can learn a graph. It's a little bit hacky, but it most of the time recovers the cognitive map of that environment, very similar to the graph that we learn using the CSCG model. One thing we noticed was that if there was aliasing, for example, this patch of this patch here is identical to this patch. This is two rooms which look exactly the same embedded in different contexts. If there are things like that, then just making predictions for the next time step was not enough to learn this graph. You needed to make enough long prediction. You needed to train the transformer to make predictions, 3 steps ahead, until it can kind of get out of this local context. That's one thing we realized while doing this. But with those additional modifications, and while I was making this slide, I realized that we never tried on anything where it was like full gray in between. I don't know whether it would work. I think we we're eager to publish the paper, so we just restricted to this kinds of more, these kinds of aliasing is much more benign, where, it's, there's a little bit of aliasing here, but, the context around is very easily disambiguated, whereas correlated aliasing, where you get a lot of gray in the middle, is much harder to learn. But surprisingly, the prediction accuracy will be pretty high, because if the most of the time it's gray, you can just predict gray for a long time, and it will make an error only during the transition. So it makes it actually the learning signal is much weaker in that setting, although the prediction accuracy will look arbitrarily high. Okay, and with that, once you have the map, of course, you can then path plan using that map. But without that map, without that graph, we weren't able to find a good way to find the shortest path from A to B after exposing the agent to this environment. Of course, this can be applied in the similar situations that we tried before of different topology. But again, I don't think we tried this heavily alias setting that we tried in the other one. So I don't know about that one. And this is just to show that without this graph, it is very hard to find a plan, even in the simplified setting. This is the probability of success in those things. I think this is in our. Okay, this one I will skip. Okay, and this is related to in context learning. So remember that I showed you that we can take this latent graph and transfer it to a new environment by just learning the emission matrix. We tested for the same thing here. So you train in one environment and see whether it can make predictions in another environment. To be able to do that, you had to train on, you keep the environment fixed and train on a whole variety of variations of that same environment. So you basically say, the same environment, I put one carpet here, learn, then put another carpet here, learn. You expose the transformer to I guess about 2,000 of such variations of the same room. Then it can, in a new variation, our discrete bottleneck can plan in that one. But if you do not expose it to all these variations, then this capability does not emerge. So if you, so there is this transfer has to be explicitly trained in this in the case of this model, whereas in the other case you could kind of use the original structure and just relearn the emission matrix to force the transfer. We couldn't find a mechanism like that directly for the transform other than just exposing it to this idea through data augmentation. Okay, so now the philosophy part. Ingredients of understanding. This is from a blog that I wrote. This is about, do transformers or large language models understand? And if they understand, is that the same way as humans understand? I don't know whether you worry about these questions at all, but this is something I am definitely interested in. And my opinion is that they understand in a way very different from how humans understand. I'm just going to try to explain what I mean there. So, these are I think ingredients of human understanding. When we understand something, it's not just language. It involves mental simulation in a world model. I typically use an example to illustrate this. If I tell you John pounded a nail on the wall, which is a natural language sentence, and if I ask you the following question, was the nail horizontal or vertical? You all can answer that question, but the way you answered that question was by imagining a John holding a nail and pounding it onto the wall. You actually ran that simulation in your head, and then you pulled out the answer. You didn't correlate with a whole bunch of sentences that you read about pounding nails on the wall. your experience of walls and nails was there somewhere in your system. It was not in your language system. It was in your sensory motor system, but the language was able to access the right simulation to run in your brain and pull out the answer, and the output, of course, comes in natural language form. But the knowledge for running that simulation was not in the language system, at least in our human brains. That was acquired elsewhere through our experience of the world. It's just accessible through language. And so, yeah. Okay, and so language is just a mechanism to control other people's mental simulations, just like he's going to control mine now. Okay, go ahead.
In your second argument, you say that cannot be acquired. One could take a stance in which language gives you like a blurry world model.
Yeah.
You can do some simulations.
Yes.
So how would you contrast your thoughts?
Yeah. So some world model can be acquired from language alone, but not the whole world model that humans carry around.
Right.
Yeah, that's a statement. Yeah.
The same applies to humans. Like if we sort of talk about atoms and we only have language that talks about atoms, our word model of an atom is very limited, right? We need to rely on machines to simulate.
Yes, exactly. Yeah. But we as humans are able to access all those other machines and make those access to other machines as our part of the world model of an atom, right? It's not our world model of an atom is not just in words. It's also in pictures. It's also our experience of looking at the X-rays coming out of the picture. Also, we made the tools to figure out those things, right? All that becomes part of the world model. It's not just just in the language, because language is a compressed form of the. So you can think of it's okay. So here's person 1, person 2. There is a whole set of world models and mental simulations in our brain. And language sits on top of that to be able to control other people's mental simulations. But they are still just at the top. A lot of things are in here, and this world model is very rich, and it has certain characteristics, which it's in a way such that you can run simulations in them efficiently. And so here is another example. Which is showing that this, I'll come to that. Okay, this world model is also very situated. It's not you need context to run the simulation. So if I give you this sentence, the haystack was important because the cloth ripped. It might not make any sense at all, although it's a well-formed sentence. In natural language, it might not make any sense because there is no context for you to run your simulation in. Your NLP system cannot parse this. Whereas if I show you this picture and then show you that sentence, you can immediately understand. You can in fact run the mental simulation and see, the haystack cannot be 2-inch thick, because then this wouldn't work. It has to be, the haystack had to be substantial. Another example of running the mental simulation. Yeah, you had a question.
Will you define world model for us to understand a little better?
Oh, define a world model? No, I can't do that. A world model is.
Can you define understanding?
Yes. So I am trying to use a bunch of words to connect to each other. Yes, that's. Let me try to explain the world model. Okay, I can. So world model is something, of course, can predict the consequence of your actions. Okay, and not just that, you can run this world model fully. So you have an associated causal mechanism within it. So you can run counterfactual simulations, not just predict the next observation given the action. So you have some kind of a structure of the world. So think of the cognitive map there. That graph is a world model of the kind I like, where you can actually ask questions about the world, which goes beyond the next token prediction. You can ask, what if I cut this link in the world? What will change about the world? So you can run surgeries about the world in your world model without actually going into the world to do it. So that's that. So so these are kind of characteristics of the world model. I don't have a very succinct definition of it. I would say I have a set of functional requirements of a world model. Yeah. There was some other question.
So I see that you are trying to connect two different worlds, I mean language and the visual system.
Correct.
And you're showing different cues, how language getting cues from the visual
Correct.
system.
Correct.
And this is about the nail in the...
Correct.
So all of this. So
yeah.
And there are some papers, I think a month ago, Surya Ganguly presented how language models and visuals, two-dimensional images, you can have a large language models on a 2D image.
Yes.
Connecting the word of language and vision is showing the, I think, path toward the word model you are trying to depict for us.
It's partially going there. I don't have a presentation of this. This world model that I drew this here. This is the vision part, and the language part. Of course, in the in a neural network, you'll have a vision model and a language model. They will connect and interface somewhere. It's not. There are some characteristics there. You cannot run this one in the feed-forward way and this one in the feed-forward way and hope to be able to run mental simulations there. The mental simulations that you can run, if it just both are running in the feed-forward way, would be limited. You have to have this chain of thought thing that is happening also happen in the visual world model, right? You cannot be just running one forward pass and say, oh, that's a mental simulation. So in the brain, in the visual cortex, anything that runs forward also runs backward. The same machinery that you're using for perception is what you are using for imagination too. So if you close your eyes and imagine a square, the things will run backward in your system. And that is related to this problem called binding problem that you can see if you test VLMs, you will see that they don't bind things very well. The language to vision connection is not very robust, and that's not very hard to understand why. Because if you just take this vision input here and convert it to a static embedding, you're hoping that all the details that you need to connect to language got captured in that embedding. But what if something did not get captured? You have to go back down in the input to get that back. So you need to have something that can access all the way down to the pixels or embeddings at different levels on an on-demand basis from the language. And so you need to be able to look back into the system to access the details as needed. So that's there aren't that many architectures that do that right now. So that could be a problem that we need to solve if you want to solve the rich world model problem. Yeah.
But if we just use lots of tokens, let's say an image, some pixels, but we will use maybe 1,000 tokens or no 1,000. Like let's try to use 1 million tokens.
Yeah.
And inference is cheap or compute is cheap. Then the problem is not there, right? Because you have.
Not sure. Like some of these things, even the simple path planning problem. As you make the world bigger, if you don't have access to that graph, I don't think you can just solve it by just some problems scale badly, even when you have lots of compute, if you don't have the right structure internally too. So yeah. Okay, so I don't know why this repeated. Okay, now you might ask, so some of the things I'm talking about connects to this Vinograd schemas things, because that was supposed to be the benchmark for common sense, and you might ask why, didn't that get solved? Doesn't that mean all the common sense problems are solved? I don't think that's true, because in my opinion, Vinograd schemas were interesting only because it was a very easy way to take this messy common sense problem and put it in natural language. But that got solved means the things that could be easily put in natural language got solved. That doesn't mean all situated common sense problems got solved. It just, even when I'm trying to test ChatGPT to test common sense, it's just so hard to take a problem and convert it to natural language. I want to say, here is a letter A with a long tail and there's a B sitting next to it. If I push A, will B move? Things like that. Putting that thing into the system itself through language looks so contrived, and it of course gets the answer wrong, but they don't look like just pure natural language problems when you put it. It's a vision plus language or a video plus language problem, and those I don't think are solved yet. So this I am saying as the minimal machinery for understanding. ability to construct rich sensory models, and it should be planning compatible. It should be able to easily plan in that model, causally structured, and support counterfactual simulations, and should be able to ability to have them modify these world models by thinking, or basically saying you can be able to run counterfactual simulations and create new structures. Active exploration based on current models, and generate hypothesis based on the world model and go test that hypothesis in the real world and then combine it and change that. Those, I think, are kind of the minimal machinery for understanding. And if the system doesn't have that, it's not human-like understanding, it's some other understanding. That's my opinion. Thank you for listening.
Couple minutes for questions.
So you give very kind of distinct environment with different colors. Did you try to tune down the colors and make them blend? Like, because eventually my guess is that the animal will pick out other cues, but things will get harder and harder. They get confused.
So the colors were a representation, just a representation. Animals typically have, their environments are not very cue-rich. They are kind of gray and some textured cues once in a while. Yeah, and they don't get confused. They are pretty good at learning those environments.
I just wonder if you make it so hard to tell the difference, whether they will eventually try to memorize the location.
Oh, but there is no direct way to memorize the location because they don't have a GPS, right? They can only access it through their sensory inputs. So, so if you take an animal and put it through they do these experiments in virtual reality all the time, like where you put an animal and let it pass through a gray corridor with one distinguishing mark, and another gray corridor with another distinguishing mark. Initially, these gray sections, the animal will be very confused by. They will think that, oh, these two corridors are identical. But after a bunch of experience, they will actually forming internal representations which correspond, these are actually two different corridors, although the local sensations for a long time are exactly the same.
So they find other cues to differentiate?
No, they don't find other cues. They basically take the same cue and find the latent context. Because if you look at the original sequences, you will find that you can create a latent structure out of them. So it's not like they are finding other cues. They are basically reinterpreting the same cue, basically saying that they belong to a different latent structure.
And in that latent structure, they're more differentiable.
Yeah, exactly. Yeah.
A quick question. One topic that came up yesterday a lot was this problem of discretization.
Yeah.
And I feel like there's an implicit assumption in much of this work that there is this kind of bottleneck. There's been a lot of work in NLP showing that these kind of models are 60 points behind kind of transformers.
Yes.
I'm curious if you thought about just the incompressibility of language in discrete space.
Yeah, that is the depressing part. The language itself is discrete. We are feeding in discrete tokens. Output is discrete tokens, but in between it's continuous. So it is surprising, right? Because the visual input is auditory input is continuous, but somewhere we are saying that we convert to discrete tokens. Somehow converting to discrete tokens for language has an advantage.
I guess I'm less talking about the discrete tokens and more like the discrete latent space that you're assuming.
Yeah, but imagine language is a discrete latent space in our brain.
I don't think that's true. I don't know.
Oh, okay. But the tokens we feed in are discrete.
Sure, I agree with that.
Yeah, right. So in that sense, the words are discrete.
Okay, but I disagree that those things follow from each other, right?
Okay. Yeah. So this is I don't know the answer to this one. In the sense that this is definitely true. That in the sense that we are not able to build discrete models with the same power as the continuous space models. That is definitely true, and it's disappointing. But I don't know whether it is because we haven't found the right mechanisms to train them, or whether that's a fundamental limitation. It's up in the air, in my mind. Yeah.
Interesting. Okay, I'm going to cut you off just because I think you did a lot of conversations. Anyone else have any other questions before we go to break? Okay.
Just very quick comment. Yeah, I just wanted to say that Stefano Fusi, he has a paper recently that says that place cells may only be memory cells. That's it, place cells.
Yeah, I know that paper. I know that paper.
Model.
I mean, it's kind of a. I don't think that paper puts place cells in the right problem formulation. Like it's yeah. So
I see. Yeah. Just wanted to know if you are aware of that.
Yeah, I'm very much aware of that paper. Yeah, okay. I would say it's more like they are looking at the vector quantization problem of place cell learning, not the actual place cell learning problem. So you can think of our model had this sequence learner and below it a vector quantizer. They are mostly looking at the vector quantizer part of it. It's almost like they are running their model in a fully observed setting. There is no partial observability in the settings that they are running in. So they don't even encounter the problem of place cell learning. They could basically say, oh, every location has a different signature. Then there's no real problem to be solved. Only the compression problem is to be solved.
Okay, thank you. Yeah.